I do have another question from the attendees. How do you see 3D integration relative to traditional scaling? That is, do you see companies choosing between one or the other for a particular design? And what factors might guide that choice? Or do you see some designs as being inherently suited to one or the other approach?
We see that scaling will continue, and there's a lot of work still happening in this area. It's costly and so on, but people are engineering their 28 nanometer technologies as we speak, and 22 will come along and so on. But there are some fundamental limitations that people are running into, and one of them is something that Bob mentioned earlier. For example, with the processors, as you go to more and more cores, and each core is going to have more and more threads, memory bandwidth is a real problem. So 3D here is something that's very interesting. So there are some aspects of design that can definitely could use it right now if the technology is available.
If you have a large block of memory, probably today more than 64 megabit, you almost from the get-go need to be looking at doing a 3D integration with a memory type device and a logic device. At 64 megabit, you have to be looking at DRAM type technologies, and DRAM inherently is, the antithesis of logic. Everything you do in building a DRAM is to the sacrifice of performance. So there is a natural match there, but I do think that you're also a lot of it are going to be not natural matches, and that's where there's going to be this kind of decision making. I think ultimately what guides those decisions is going to be cost. If the answer is you can do it in 22 nanometer, but 22 nanometer is more costly than building two 45 nanometer parts, for instance, you're going to build two 45 nanometer parts with TSVs and put them together. Today, TSV cost is expensive and it's hard to get. I think we, yet still during, are the only suppliers of TSV wafers in a quasi-commercial format. But 5 years from now, you'll probably be able to get TSV wafers from every fab. And the cost is likely to be on the order of another metal layer. It'll be $50, $60. So I think the direction that it's going is that it's going to be a very viable cost alternative to shrinking.
Bob, to continue along what you were saying, when you look at high-performance devices or really scaled devices, typically it's one portion of that entire chip that requires that kind of technology. Right? And what TSVs allow you to do is, again, take away, the high-performance portions which really need it. You run it in the fab where, you got that kind of technology capability, and the rest, if you don't need it, you run them in an older fab, and that
works
gives you a
very
degree
well.
of freedom. Exactly.
If you want to build the fastest possible devices, and I always pick a fight with people on this, you go build it in 110 or 130 nanometer technology, because that is the fastest transistors and interconnect structure you can build. As we've scaled, it isn't faster. It's lower cost, it's higher density, it's lower power. There's other things that you get from it, but you're not getting the highest performance. If you want to do analog or mixed signal, 130 nanometer and up is the right answer.
6-inch wafers, 8-inch wafers.
Absolutely. You really need to look at the sum of what you're trying to build. It's the same thing that's driven the wire bonded SIPs. People didn't do that because they liked complicated engineering, but they figured out that it was cheaper to, buy a flash memory and do the processor at 65 nanometer or 45, and your power amps out of gallium arsenide or silicon germanium, and you wire bond them together or flip chip them together. Cost will drive it.